Так, есть. Ой. Ага, вот Маша послушала. Так, хорошо. Вот. Так, попробуем регулировать расстояние. Мне кажется, сейчас будет нормально. Сейчас я вычеркну места, где нельзя писать. Ну, тут, в принципе, легко понять, какие это места. Вот. Ну, вот, скажем,
Ну, на самом
да. Да, ну, то есть вот все, что здесь. Что здесь нельзя писать, здесь нельзя писать. А здесь, сейчас я чуть подвину, и можно будет писать в других. Так, здесь вот, пожалуй, вот здесь. Вот, все остальное видно. Я думаю, что можно начинать, потому что уже... Да. Ну что, Маша, в общем, мы, в принципе, начинаем. Кстати, давайте. По-английски, пожалуйста.
Yes, let's start with the first problem, which is the following. Let omega is like a n-dimensional complex vector space. We and consider a homomorphic map. From omega to C2, such that the image of omega is contained in the union of two complex lines. So we need to show that, in fact, the image should be contained in just one of these complex lines. So we have an open domain, which is mapped into say the union of the complex lines. Let's denote them by C1 and C2. So any guess on what we should use here? So in particular, what do you know about images of complex domains under holomorphic maps?
So some hint here, it is it will be helpful to use the material of today's lecture.
Yeah.
This sounds sometimes.
Yes.
Sure.
I have a question.
Yeah.
Like, I think the image of A should be open.
Yes. And
Is it possible that two lines contain the open subset of C2? I just think it's impossible in R2, so I'm not sure about C2.
No, because the open space was brought only for maps to see. And we can work function. Наш готовый сейчас. Давайте.
I hope you can do it. Two lines and let's denote like C1 without C2 is 1, C2 without C1 is 2. And so suppose we have V1, which is was V1, and V2, which is and suppose both of these subsets are non-empty. Then they are open because it's a continuous map. And we know that if we have, so let's consider like, I can say that F is like F1 and 2, right? And I can say that F1 on so that's like C1. Okay, just one change of coordinates. Can I say that C1 is I can have a change of coordinates and say that C1 is Z2 is equal to 0 and C2 is Z1. Okay, so if I take F1, so I'll just think a moment. So if I take F and I regard it as a function on W1, then it's a function that its image lies in C1 without C2. So its image lies in C1. So that W0. So this is 0, right? Because F2 of 1 of F inverse 1, not V2, sorry, V1 is 0, right?
Just a moment.
So when you write down F2 is 0, do you mean that you introduced new coordinates?
Yes, I say that.
Yes.
C1 is
Exactly. Yes. Yes, exactly.
So that's true.
Yes.
Okay. Then that's another subset inside omega. Then F2 is equal to 0 everywhere.
Yes.
And then the image lies in. And I can say the same thing about V2. So I can say that F1 on V2 is 0, then F1 is equal to 0 everywhere. And then F is just equal to 0.
Yes, exactly. Yes, thank you much. So the arrangement is the following. So suppose that the image does not lie in single line. Then one of the two subsets. Then one of the two pre-images, either V1 or V2, is non-empty. Some of them is non-empty. So then if it doesn't lie inside inside a single line, then both pre-images are non-empty. They are open. And suppose that these lines are coordinate lines. Z1 equals to 0, Z2 equals 0. This doesn't cover the case of parallel lines, but for parallel lines it's just impossible by the connectivity.
Absolutely, it's the easy way.
Yes, so there is always a possible case that the lines, and then one and V2 are open and non-empty. And on V1 we have F2 equals 0 identically, and therefore by using some analytic extension, F2 equals to 0 everywhere. And similarly, F1 on V2 equals to 0 by definition. And therefore, it is equal to 0 everywhere by uniqueness. And therefore, F1 and V2 are both equal to 0, and therefore, F is constant, sending to 0 everything. And the 0 lies in both lines. And in particular, one can say that the image, the trivial 0 image, lies in a line of features.
Yeah, I believe that it's more better to say define W1 and W2 like C squared without it. So it's literally they are real,
Yes, exactly.
open subsets in C2, and then
Yes.
they are completely.
Yes, it's exactly the same. Yes, same. Yes, thank you. So,
Yeah, sure. So let me try it right here. So I suppose on the lecture you have seen the Hartle's extension theorem for two variables. So just the same statement in several variables. So let's fix some notation. Okay. such that or KB just the multi-radius. And the same. So if it's first k radii and the last n minus k. And fix an open subset inside the polydisk delta Rn minus k. So and consider so let me write this down and then I will explain. So these are two subsets inside C n. So and that omega be by definition the union of A and B. So this is what is called the Hartree figure. In dimension n. Yes, we take a polydisk and for k coordinates, we take a polydisk and throw out a smaller, a closed polydisk of smaller radius and multiply by polydisk in plus n minus k coordinates. And here we take just the product of this polydisk with a fixed order subset. So we need to prove that any function which is holomorphic on omega extends to a holomorphic function on the polydisk. I suppose you have seen this in two variables. So here the situation is more or less the same. So maybe just a two-dimensional picture. Is somehow representative of what happens in any dimension. So we have this B here, and we have and A corresponds to this part. But you'll need somehow to rotate this picture around this axis.
Yes, so the statement of the problem is formulated. Given a domain called Hartog domain, main dimension, proves that any function in this holomorphic on this Hartog domain extends to a holomorphic function over the whole unbound polydisk. That's the problem. In lecture, we have done this in 2 dimensions, but now the problem is to do this in any dimension.
exactly the same as case.
Yes, so you're right, Masha, so the proof
Yeah.
is just basically the same, but formally speaking, if you have to change some subject to some
Just have to change delta to what variable delta.
And how do you extend the function?
By multi-variable Cauchy theorem.
Please write down.
Yeah, so maybe it's exactly the same,
Just rewrite it. Yes.
to here have integral over the product of yeah.
So yes, it is product. It is not just a single boundary of single, it is a product. Yes.
Yeah.
It's just a multiple integral. Just write down several integrals.
Yeah, correct.
Okay. Thank you.
Yeah, so the idea is the same. You take a point here and you write down the multidimensional Cauchy formula using a contour which goes in this inside this domain. And just by a related continuation, you extend the function. Okay.
So there are several problems. I think maybe we will not have time to solve all of them, but maybe we will. You can choose any order of presentation of this problem.
Yeah, so probably it will be easier to go to problem 4.
Yes.
It's, so that omega inside C3 be a domain. And let again C, no, not C, but L inside C3 be a complex line. And to prove that, a function f, which is holomorphic on the complement that you write like that. So we intersect the complex line inside C3 with the domain, and we take a function which is holomorphic on the complement. And, a function always extends to a holomorphic function on yeah, of course, just for the program to be non-trivial, we need to assume that actually the intersection is non-empty.
So each function holomorphic in a complement of the line extends holomorphically to all the points of the line.
So just know that the problem is local, right? So you just you have the points where a complex line intersects the domain. And you need to extend the function to every point in this intersection. So the problem is local. You take a function which is defined on the entire complement, but you can just restrict a small neighborhood of a point.
So I believe that we can say so we can definitely assume that on this ball disk, and then we can assume that the line is like Z2 is equal to Z3 is equal to 0. And then we can say that for every fixed Z1, we have a theorem from Glutsyuk about this compact. I forgot the word.
Maybe you can draw a picture.
Yeah, so we talk about politics.
But just Masha, please draw on the
Oh, sorry.
Somewhere.
Something is wrong here.
So you can erase everything about what is going to happen.
What?
Yes.
So we know that for every fixed square here, every fixed two-dimensional polar disk, we have an extension.
Yes, we have an abstraction.
Yeah, we have an extension. So we know that we can define a function on this line, but we don't know yet that it's holomorphic. We know that the result is holomorphic on each such square?
Yes, on each slice, transversal to the deleted line, on each slice, you have a function with isolated singularities.
Yeah.
It's the intersection point of the slice with the line. And we know that the function of two variables cannot have isolated singularities because isolated singularity is a common singularity which can be easily erased by
Yeah, so on each slice we now have a holomorphic function.
Yes.
And and I believe that on each slice it's continuous, so we have a continuous function on the whole thing.
On the slice it is continuous, but why it is continuous? It is so we have to find to show that thus extended function is holomorphic and in particular continuous, but continuity is a priori not clear. Even continuity is a priori not clear.
Yeah, I think I have to think a little bit.
Yeah.
Sorry.
Yes, but Russian point is correct.
Yeah, maybe a small hint.
Yeah, so but it's continuous on. Oh, no, so sorry.
A small hint is that it's not a coincidence that they've given this program right after the Hartley's theorem. So maybe you can. So again, everything is local. So you can choose coordinates. Really.
Okay, it's just Hartley's theorem, so we just fix L1, like positive L1, or positive, oh no, we fix, just a second, this, reason minus kind of three-dimensional, so we fix k equal to 1, we fix, no, not equal to 1. Sorry.
So I think the idea is that you want to pass to local coordinates and draw a Hartley's figure. So if you fix a point in the intersection, and in order to extend the function, you need to draw a Hartley's figure inside a small body disk.
No,
which is
the small r is equal, the k is equal to 2.
correct.
The small r is just something positive. We don't actually care.
Yeah.
And
It's not.
and v just doesn't intersect with the line. With the line doesn't intersect with the z. With this z2 equal to 0. So v is just like s. No.
It's just we're taking this.
V is just like, so we can say we can take a plane which is parallel to this. No, we need some code, but sorry. So this is 1, this is 2, and that's the 3. And so our line is 0 is a constant in Z1, constant in Z2. And we fix V inside Z2. We just can fix V equal to Z2 not equal to 0.
So V is taken as one-dimensional domain, right?
Yeah, V is like
One-dimensional.
this.
It is in the second factor, yes?
Mm-hmm.
Okay.
So that's like
Okay, so it is in C number 3, you mean?
mhm.
Okay, so C, one moment, you consider C with coordinates 3?
No, sorry.
I doubt.
So something's wrong. So this three is no, it has to be
So what is K? What is your K? Your K, what is your
K
K?
is equal to 2.
Yes, K is equal to 2, that's correct.
And so
Yes.
Z1 and Z2 not equal to 0. That's like this. Like something not equivalent to the bound. And the last one, so we need V, which is which we multiply by this square. Oh. No, we don't have to multiply. We work square.
No, because the point is if you take Y in V, if V lives in C with coordinates 3,
Yeah, that's wrong. That doesn't work.
why doesn't matter actually? No, in fact, what happens if you take the horizontal slice with Y equals constant or Y, then this slice will definitely contain, intersect your line. So,
So that's program to let's fix it. We need what do we need? We need it can be equal to 2.
actually, it's not clear. It's not clear what we could choose for the K. It's not clear. So maybe one can take a different K.
Yeah, it's like
Yeah, probably you should try to.
Yes,
equal to 1.
yes, that's right. Yes, if you take,
Yeah, we would just take 4,
yeah.
and then we'll have like V. So we can take the K equals to 1, and then we'll take this picture, which means and we take V like that, but inside C times C. The second C and the third C. And we take 1 greater than 0, and then it works because then V multiplied by the first C is just like everything without this plane, and this, and that's just
That's correct.
the slice like that. So there's like this part and this part. So these are slices parallel to this.
Yes, so yes, so it's correct. So if you choose V like this, then let's consider the corresponding set call it V. Yes, it corresponds to set B. Just if you take V, then you find out that V cross D is a disk of radius R1. This guy will be disjoint from the line, just by definition, because on the line Z2 should be equal to 0, but it is distant from Z2. So on B, we have holomorphicity. And now let us take A. A is the product of the complement of a disk centered to Z at 0 in one variable, in first variable, times everything else.
Yeah.
And here we can find this set, which is known by A, will be disjoint from the line because on the line Z1 equals 0, but in our set, which is a product of angles centered at 0 times everything else, this product is disjoint from the line because on the line Z1 equals 0, while on the angles on the first factor is not 0. So everything is fine. So we are exactly in the context of Partox's condition of Partox's theorem, and therefore the function extends everything. So thank you.
Yeah. And in fact, this line of proof is can be generalized to say if you have a domain in C to the n, and you don't have take something which is a complex line. Just if you have so everything is local, you can take a point, and what you need is just if you take a submanifold, which is locally which is given by some holomorphic equations, but again by a holomorphic portion of the inverse mapping theorem, locally it's just if it is some manifold, it looks like something.
Yeah, so
It's given by locally by linear.
Sub-zero has to have a dimension at least n-1.
Yes, so the important point is that the complex codimension should be at least 2. So in general, you cannot extend to a hyperplane.
Because the hyperplane is a decent set of zeros.
Yeah, correct. So you can take a function which has a pole.
So basically, we just proved that we haven't really proved it, but the same idea proves that the complex codimension of the submanifold of zeros of some function is 1 if it's not constant, right?
Yes,
Can you do?
yes, that's true. If you
But
take a
it's
function,
Yeah.
the zero locus of a function is something of complex codimension 1, always. Always provided it's an analytic. Always. It's analytic set of codimension 1 with open and this regular part.
Because there are some problems in the past when it's not submanifold, like when the derivative of the function is 0, and we can use I just неявных функций.
Implicit function theorem.
Implicit function theorem.
Okay, and that is there is one more problem for today, which is about a general theorem on erasing compact singularities, or about extension of holomorphic function to across a compact subset. So that omega then being connected. Domain. And so let us take a subset which is compact. Compact subset such that its complement is connected. Any function which is homomorphic. The complement extends homomorphically from so an example is just a complex ball. And there is one more so actually we don't need to consider the general case, general omega. Just for simplicity, let's restrict to case by complex ball. And the next case, which is somewhat more difficult, is the following. We consider a domain which is such that there exists in general, we can prove this for domains such that there exists locally a differentiably trivial vibration so omega is diffeomorphic. To a product omega n minus 1, where this is some open domain of dimension n minus 1 times some open domain U in C.
And I believe that in the domain in fact, it is assumed that the fiber should be simply connected.
Yeah, probably. Yeah, it's the most.
Yes, so the fiber cube is simply connected.
I'm not exactly sure what you have given the lectures. What version?
Of the lectures, I will give the version of this statement for the case when OW will omega is polydisk. And that's it. It's just the statement which is reduced to Karpov theorem.
Okay.
But here the proof is not a direct consequence of Karpov theorem. It's not a direct consequence of the statement of Karpov theorem.
Well, yeah, you need to modify it.
But I guess whatever omega is, you can do a biholomorphic function from Cm to Cm and then make omega a polydisk.
No, in fact, what's happening in more. This is the difference between one variable and several variables. Because in one variable there is frequent bucket theory.
Yeah,
Which
you
says
said that.
that every simply connected domain in C different from C is conformally equivalent to the unit disk. In one dimension. Two dimension, it is very strong false. If you take an average domain in C2, then there is no chance. Just if you take two average domain in C2, there is no chance with zero probability they will be biholomorphically equivalent. For example, a polydisk is not biholomorphically equivalent to the ball. We will prove this theorem in our course. But I will tell you a bit more. In C2, you can find a strictly included subdomain. You can find subdomain in C2, which is biholomorphic to C2 itself. So-called photobiograph domain. In one dimension, the stem happen by Riemann matrix theorem. But here it doesn't say the biholomorphic type of omega is not, it doesn't matter much. But in fact, so the statement of Karpov theorem is not applicable as it is. One can use some ideas previously discussed in lectures, some other statements to try to give a proof. Even if you manage to do this in the case of a complex ball, I mean that you will manage to do this in the case B, which is slightly more general. Let us treat the case of ball. Пожалуйста, не стирайте больше.
Да.
Ставьте, пожалуйста. And without loss of priority, you can consider that your compact set is just a small group. You can just include K in slightest in a ball which is in between. Because of compact factors. And this will give a very strong statement.
By
concentric ball.
some ball of radius r.
Yeah.
which is closed.
And contains.
We use just radius because we can take each point, take some point on the boundary of this ball, and we can regard a small polydisk which is contained in the VM or non, and use the theorem for polydisk. Then we have an extension to this polydisk because it is connected.
It's connected and what so much order.
No, something. No, that it doesn't contain. This is not contained. No. It's not contained.
So you can try to extend to at least one point of this ball. To at least one to boundary point of the ball VR. And if you understand how to extend to at least one point, then I think you will manage to extend further on.
So let us fix points.
Just take a point in the boundary simplicity. Yes.
I believe that what we really need is what we need to prove the kind of theorem one would have. No? Just
Actually, to extend this point, maybe you can use kind of Hartog's theorem, maybe.
do you need for Cauchy's formula?
Yes, actually, yes.
Do you need to be true the whole logic on the whole polydisk? We can, because in one-dimensional complex analysis,
Yeah.
if I'm not mistaken, we have this Cauchy formula for a ring, not for a.
Cauchy formula, yes, we can write the Cauchy formula for ring, yes, true for disk, for ring, yes, we can write down Cauchy formula.
Yeah, so if you write it for a ring, then we can just prove, we can follow the proof of Hartog's theorem. So we can like look at this ball. So we can have a ball. And look at the ball inside. Okay. And there's something weird going on here, so we don't know what's happening here, and the function we defined on the boundary, not on this ring. And we can just take some small slice and even smaller slice and regard this ring, write Cauchy formula for it. Why don't we have some colors for this function? Right.
Yes, we can do this, yes.
Yeah, and write down Cauchy formula for it. And in this way we can define the the function on this slice.
Yes.
And then we can just look at all the slices and define the function on each slice, and they must match because of the uniqueness of analytic extension.
That's true. That's true. This works. This works.
No, but how do you prove that the function extent is homomorphic?
Because we define it as a Cauchy formula. So we just take some delta here. So write down just a second. Okay, so I'll say that like this thing, this multi-radius is delta, and I write down I'll define the function like this. I'll define.
So then it's slightly greater, bigger than R. Or what is that?
It's slightly bigger than
R small.
R small, and it's slightly smaller than R.
Okay, yeah, so that would be a ball of radius R, and this is R.
I believe that's not what we really need, because I wanted to. Okay, so let's first think about this slice in the middle, because for these slices we have this other R's. So this like okay, let's define. So I define my function. Oh, sorry, I can write here. What can I write? Oh, can I raise the same idea?
Yeah.
So we define this function as a and here I put my function of say I
What is K-bar?
M.
So you're writing the highest dimensional Cauchy formula, yes?
Just a second. I think I'm not writing the highest dimensional Cauchy formula. No, M-1.
Okay. So you consider the vertical slices by.
So that's what M.
Okay. Okay.
And here that's delta I, and I write it like Ci minus Zi product. Okay, and we didn't prove it, but I believe that should be similar to the one-dimensional case, that inside this ring or this cylinder, this function should be equal to f.
That's the idea is correct. Yes, it's correct.
Yeah, and if we do it, then we've done it for this middle slice, and then we can take any slice. We just need to have delta, which is like we need to put this ring inside this messed up ring.
So Masha, so I believe that the integration variable should be from the 1 to n-1, yes? So you integrate, so z1, say here you have n-1.
Sorry.
n-1, okay. Okay, so you integrate on horizontal. So, and if f of z1, etc., z-1, and zn, yes, and z, so f is from z1, etc., zn-1, and zn.
Yeah.
Yeah, so it depends on all this.
And zn, yes, that's it.
Yeah.
That's correct.
But we have to prove it because we haven't.
Yes, so delta is R. Okay. But Masha, I have a question. So delta is chosen dependent on the slice or what is it?
Yeah, it's dependent on my slice. So it has. So
okay,
I just
tell you let's write down if you consider slice that n equals.
yeah, just a second. I believe I need some more notations. Suppose I take a slice from something.
Erase.
Yeah.
Erase.
Oh, I can erase this. Just explain what I mean by slice. So I'll redraw this picture, and then I take a slice. So the slice is looks like this. So that's some
Zn equals constant.
Zn equals C, and Zn equals C plus epsilon. And I have to choose epsilon and delta such that for
So Zn equals C, then I know Zn equals 0. You do mean that Zn equals C is central slice? Yes. If the central slice, let us put.
it's not a central slice, it's just some arbitrary slice.
Okay.
So C is some arbitrary number.
Okay.
So I need to see that for any R1, Rn minus 1, and Rn are such that is R squared, because this R is the radius of this ball. And for any big R's, and with the condition that Rn are here in that one that not C and C plus epsilon. It's true that this implies that R1 plus R is
Is C positive number?
that's now it works only for the two-dimensional ball.
Okay, let's do those in 2 dimensions.
Yeah, let's first think about two-dimensional case. No, and then we have to do it by induction. It's complicated.
Yes, okay, let us do this 2 dimensional.
Let's do it in 2 dimensions. So n is equal to 2, so it's 2, 2, 2, 2, 2, 2, 2. R1, R2. Here, then R1 is less than delta 1 less than 1. That's the two-dimensional case.
So delta is like this, delta 1 is like this, okay?
Yeah, so we choose delta and then we complicate this formula. Then just I don't know how to prove it. I know how to prove it in two-dimensional case.
So actually, Masha's idea works.
Works
You
for two
just,
dimensions.
Yes, it was an innovation, but I would like to since the time is over.
Yeah.
Yes, yes, пожалуйста.
But like you still integrate over a hard disk.
Or polydisc, or which polydisc?
The
Yeah, here, what is.
side.
Or on n-1 dimensional polydisc, yes?
Yeah, so you still
Yes.
integrate on a hard disk, but is it true that we can find a hard disk between these two boards?
Нет,
It's
no, no, no,
true
no.
in Killer it's not true in
Yes.
machines.
Yes.
Like we just consider the two-dimensional case, and this is a little r, this is a capital R. Then you might find delta here, right?
Yes.
And actually, what's the disk is looks like this.
But is this disk okay? But if the disk does not contain it in the ambient ball, this disk goes away.
Sorry?
This polydisc goes away from the ambient ball. In general, the polydisc goes away from the ambient ball. If you consider the n-dimensional polydisc, this goes away from the ambient ball. Because you have this corner. This corner is out of the big ball.
Yeah. So how could you integrate here?
This is foolish, but just
Choose Zn from some range.
so Masha says the following: you just take a slice. If your slice is here, it is disjointed from the disk. Yes. If you can write down, because you can choose a circle, you can run down Cauchy. Cauchy is an iteration along this corner.
Yeah.
It's perfectly holomorphic. And this point can be moved down. But the new slice, along the new slice until the slice equation will intersect the crossed out wall. But the Cauchy integral remains well defined. And this extends your function inside here. But it extends just slightly here. Once you extend here, you can do the same extension just along. You can draw a cylinder whose complement cuts out some small bosses here and there. You can consider a cylinder. You can extend everything to the complement of the cylinder. So you consider a cylinder. You can extend which contains almost whole wall, but without some small bosses here and there. And you can extend. So you can write down your Cauchy formula, which extends your function to the complement of this cylinder here. Yes. Yes. And you can proceed. Once you extend it to the complement of the cylinder, you can take your Cauchy formula obtained from the first step with boundaries slightly more remote here. You can write down Cauchy formula with boundaries here.
But,
and you can move again like this.
Yeah, I understand this idea,
yes.
But I guess it's more like a circle and not a poly.
And now, just to familiarize everything, I suggest the following. I suggest to consider 3 balls. So this is cross-out ball, and you consider it intermediate ball. And the formal definition of extended function will be the following. You take any slice, whatever slice you take, you mark its intersection with the boundary, with the boundary of the intermediate ball. This guy is this is you reproduce it here. You write down Cauchy formula is this boundary. So you just take the closest intermediate sphere like this, and you write down Cauchy integral f. So the integral over 2 pi, we are in 2 dimensions. Integral here you integrate along. You know this slide by so Z2 equals 1, and you integrate sphere with Z2 equals some y. So some you integrate along the intersection of sphere with the level Z2 twice. Yes, that's it. And here you put f of Z1 Z2 over Z1 minus Z1. That's it. And this is one. A priori, this guy is not holomorphic. But in fact, it is holomorphic. This guy is not holomorphic. But in fact, what happens is the following. Since you because it is holomorphic in Z1 inside. But what about holomorphicity in two elements? Because if you look here, the function depends on the parameter, which is this parameter. The choice of this of the range of this parameter depends on the two.
Yeah.
But the point is the following: if you take two neighbor slices and you take integral along this, I claim that it is the same if you integrate, if you just push your away, if you change the integration contour, if you move the integration contour away, the value will remain the same. By Stokes' formula for the angles between these formulas. And therefore, but if you move the boundary above, you can just move it parallelly there. And therefore, locally, the integration result, if you just integrate on the sphere or just along some constant on the one boundary, the result will be totally the same. And that's where the holomorphicity comes from. Because locally, this value is independent on the choice of contour integration along the development. That's a question. So this is formal definition of just this integral sphere. But maybe the local argument that Masha suggests, we managed to prove that it is indeed local. So Masha is the case. Yes. Okay. It's kind of more, it's more tricky than Hartog's theorem, but still.
We haven't proved anything, we just proved it for m equal to 2.
Yes. Yes, that is a proof in general case, it's the same.
Not exactly the same. We have to integrate by sphere. And
sphere, yes, exactly, by sphere, and that one will be last dimension. Here. In high dimension, that one will be multi-dimension.
Yeah, we don't integrate it by quantities, so we can use the Cauchy formula.
Yes.
We have to use this.
And by the way, we can do the same, but we can still keep the one will one dimensional and the two will many dimensional.
But if we just integrate on arbitrary conscious,
yes.
We can just we can forget about the two. We can have this psi just going around all this sphere.
Yes.
But then we have to prove that that's the same and the analog Cauchy's formula works.
But it is just an abstract Cauchy integral, which coincides with our function when Z2 is erased from the height of this. If Z2 is here, then everything is fine. The integral, the Cauchy integral coincides with your function. If Z2 is high enough, such that the slide Z2 equals constant doesn't intersect the erased ball, then the Cauchy integral written here coincides with the value function, with the value of initial function.
I believe that we have to. I believe that I get what you're saying, but that we have to say it again next time because
yes.
something is just being.
Yes, but because this integral makes sense, and what happens is it coincides with our function on some domain, here.
Yeah.
Yes.
I get it. I believe you, but
the whole issue is holomorphicity of this formula. That's foolish. Once you have holomorphicity of this formula, everything is done. And the holomorphicity is proved just by this local argument of moving boundaries. if you just write down Cauchy integral, if you take two domains, here and there, and if you take just it's in one variable, if you take just z here, you can just integrate Cauchy form, so it is just S1, S2, f of zeta, the integral of S1 divided by z minus z is equal to the integral of S2 of the same value. Provide and if this holds if f is just holomorphic in the annulus. If f is just holomorphic in the closed annulus, this equality holds true. By Stokes formula.
I get it.
Yeah. Okay.
Это какой-то все-таки, это же издевательство, мне кажется, чуть-чуть здесь не так. В смысле, не то, что здесь что-то фундаментально не так. В смысле, я понимаю, что вы говорите, но мне кажется, что это какой-то очень... Чуть в этом есть... Не знаю, сказать. В общем, по-хорошему, может быть, можно просто интегрировать по сфере, которая вот такая же, тоже размерности. Есть граница Омега. По сфере размерности N-1.
Yes, actually, what happens is that in the most general setting, without any assumptions of vibration, etc., I know that this is proved by using Bochner-Martinelli formula with integration of something along the boundary. This formula exists.
По-хорошему, нам все-таки надо это, чтобы не издеваться над индивидуальской, нам нужно доказать формулу Каши не только для Кулидинского, а для вообще какой-нибудь такой относительно произвольной истории. Ну, то есть у нас есть принцип контур, да, у нас есть значит, в окрестности этого контура внутри, значит, все было можно. Значит, наверное, тогда у нас верна формула Каши. Наверное, это даже такая система, как вы говорите, что дальше нам надо это, значит, вот нечто, короче, значит, здесь, может быть, сделать в следующий раз, потому что, иначе ощущение какой-то обман, что мы на самом деле пользуемся маленьким кусочком некоторой большой теории, хотя при этом доказывая ее исключительно в частном случае.
Да, то есть на самом деле, Маша, я думаю, что вы правы, и что, если есть желание, можно разобрать на семинаре формулу Бохнера-Мартинелли.
Вот, давайте сделаем, потому что мы явно сейчас пользуемся ей. Я не знаю, что это за формула, но, судя по вашим пересказам, это примерно она. Вот,
не совсем. Это не она, то есть она, кстати, по-другому, но она есть. То есть это именно есть такая формула вот, с интегралом чего-то по границе. Вот.
Да.
В общем, давайте с этим как-то разберемся.
Да, конечно.
Это должно прям следовать.
Да. Ага. Да, это было бы хорошо, да.